So for the second project, I decided to do number 75, which states to prove that if d1 and d2 are distances, and that t is an interval from 0 to 1, including 0 and 1, then dxy, which is defined as t times d1xy, plus 1 minus t times d2xy, is a distance, which means we need to meet all four conditions of a distance. So for the first condition, we want to show that dxy is greater than or equal to 0 for all xy. So we know since d1 and d2 are distances, d1 is greater than or equal to 0 for all xy, and d2 is greater than or equal to 0 for all xy. Also, since t is in the interval from 0 to 1, 1 minus t is greater than or equal to 0, and t is greater than or equal to 0. So then, t times the distance 1, xy, is greater than or equal to 0 because t is greater than or equal to 0, and d1 is greater than or equal to 0. Also, 1 minus t times d2xy is greater than or equal to 0 because 1 minus t is greater than or equal to 0, and d2xy is greater than or equal to 0. So this whole thing, t times d1xy plus 1 minus t times d2xy, is greater than or equal to 0 for all. Therefore, the distance defined, xy, is greater than or equal to 0 for all of xy. So this meets the first condition. Okay, so for our second condition, we need to show that the distance from x to y is equal to 0 if and only if x is equal to y. So I'm going to do the easy part first. So let x equal y. Then t times the distance 1 from x to y is equal to 0 because d1xy is equal to 0 because it's a distance, so if x is equal to y, then that's obviously 0. Also, 1 minus t times d2xy is equal to 0 for the same reason because d2 is a distance. Therefore, the distance from x to y is equal to 0. Okay, now for the hard part. So we're going to assume that the distance from x to y is 0. So then t times d1xy is 0, and 1 minus t times d2xy is 0. And that's because all of these terms are greater than or equal to 0. They can't be negative, so we can't have additive inverses. So if t equals 1, then t times d1xy is 0. Wait, sorry. This implies that I'm skipping around here. d1xy is equal to 0, so x is equal to y. Back up here. If t is less than 1, then 1 minus t is not 0. So d2xy is equal to 0, therefore x is equal to y because it's a distance. If t is between 0 and 1, then t is not 0 and 1 minus t is not 0. So d1xy is equal to 0 and d2xy is equal to 0. So x is equal to y. Therefore, x is equal to y. And we have proven that the distance from x to y is equal to 0 if and only if x is equal to condition. This one could be a little hard to understand because there's so many variables. So we're going to prove, we want to show that the distance from x to y is less than or equal to the distance from x to z plus the distance from z to y. So we're going to let x, y, and z be in the metric space. We're defining the distance from x to z as t times the distance d1 xz plus 1 minus t d2 xz. And we're defining the distance from z to y as t times d1 zy plus 1 minus t times d2 zy. So, since d1 is a distance, d1 of xz plus d1 of zy is greater than or equal to d1 of xy. This is what we're trying to prove for the distance that we've defined. Similarly, since d2 is a distance, d2 of xz plus d2 of zy is greater than or equal to d2 of xy. So, the distance from x to z plus the distance from z to y is this whole mess. It's t times the quantity d1xz plus d1 zy plus 1 minus t times the quantity d2 xz plus d2 zy. I basically just factored out these two things. So when we look at it, this is what the distance from x to y is, this definition, and this is what we have right here. So if you cross out all of the t's because they're the same thing, it's the same term, you can cross them out. So this doesn't matter, this doesn't matter. When you're looking at, is this less than or equal to? We know that d1xz plus d1zy is greater than d1xy. We also know that d2xz plus d2zy is greater than d2xy. So these two things are greater than both of these two things, so this whole equation is greater than this one. Therefore, the distance from x to y, because this is what we have up here, is less than or equal to the distance from x to z plus the distance from z to y. Okay, last condition, we're almost there. This is actually one of my favorite conditions because it's really easy. So, the fourth condition, we want to show that d of xy, the distance from x to y, is the same thing as the distance from y to x. So, we're defining the distance from y to x as t times the distance 1 from y to x plus 1 minus t times the distance 2 from y to x. So, since d1 is a distance, d1 of yx is equal to d1xy. Similarly, since d2 is a distance, d2 of yx is equal to d2xy. So t times d1yx is equal to t times d1xy. Also 1 minus t times d2yx is equal to 1 minus t times d2dy. So then, the distance from y to x is equal to t times the distance 1 from x to y plus 1 minus t times the distance 2 from x to y, because we did the substitution right here, so we're using this so we can substitute it into this equation, which is coincidentally what the distance from x to y is. So therefore, the distance from y to x is equal to the distance from x to y. So, all the conditions, this distance satisfies all of the conditions to be a distance, therefore d is distance, and we're done.